Hello and welcome. So, quick question. Or by raise of hands, who here writes fast software or thinks they write fast software? Who here thinks they write kind of fast software? Who here thinks they write slow software? Who here thinks they don't write fast software at all? Now, I'll get to that in a moment. So, thank you to the amazing sponsors for which DDD wouldn't happen. And who am I? I'm the founder of OfficeFloor. So OfficeFloor is an inversion of coupling control container, a bit like inversion of control, except that it takes it further. It takes it not just only to dependency injecting objects, it injects threads and it injects functions. And it's a different way of looking at things and solving many of the underlying patterns. But if you want to know more about that, see my previous DDD presentation. Today, we're talking about OfficeFloor's web server. Now, the first question you have is, why write a web server? There's so many of them out there, and OfficeFloor, being an inversion control container, can inject them all in and use them as necessary. So why did I go to the effort of actually writing an own web server? Well, it comes to what we're doing more and more with our modern day apps. Now, if you have an SPA application that loads up and starts firing requests at your server, the specs actually say your browser is only allowed to have 2 connections to the server. Now, some of the browsers have pushed that further and gone 4 to 6 and 8 in very rare cases. But they limit the number of connections to the server. So if you've got 2 requests going down on 2 connections, the big problem is the web server will only service one of those requests off the connection at a time. So if you've got 2 long-running requests and lots of requests behind it, you get loading on the page. So what we've done in OfficeFloor is that we process all the requests off the connection concurrently. So as the requests come in, it processes, it doesn't just do one, it actually processes more and more and more. And what you get is you get reduced latency. So everything just gets processed and then sent back to the front, and overload is handled by thread injection. And again, topic for previous conversation. So like all things on OfficeFloor, I get sidetracked. Kind of came across the Tech Empower benchmarks in 2015 and thought, hey, I can do good at this. Submitted my results and went, ooh, that didn't go well. And let's not talk about that. But since then, and in the last round 20, been doing improvements, in the last round 20, I've become top 20. And there's the 6.4 million requests per second. And there's about 122 servers entered, and the next round 21 will have about 126 servers entered. The number's always growing. Everyone thinks they can write a HTTP server. And, just like myself, and just recently I changed the database driver and now sitting in top 10. And hopefully keep that position for round 21 and I'll be in the top 10 officially. So, how did I do that? Well, first off, let's get this out there, programming languages have nothing to do with it. OfficeFloor is written in standard Java, non-blocking I/O. There's no special libraries or anything. It just simply uses the standard socket libraries and does what it needs to do. And if you want to argue that programming languages have nothing to do with it, rank number 2 is Just, and it's written in JavaScript. So the question comes down to, what dictates performance? Well, I do not write fast software. Hardware deals in speed. Hardware has better clock cycles, increased bus speeds, faster networks. Software deals in efficiency. It's instructions to the hardware. No matter how many instructions I can send to the hardware, I can't make the hardware go faster. I can only be more efficient in my instructions to that hardware. So now I need to understand hardware, and I'm not an electrical engineer, and there's all these things, and there's this. We don't need to understand it heavily. What you need to really focus on to get performance is to get your data to the CPU. The more data you can get to the CPU, the more you can process things through, and the quicker you can get your performance through. So then I was sitting there going, well, how do I explain this? Because everything's measured in milliseconds, microseconds, nanoseconds, and I really can't get a feel for that because I've never experienced a nanosecond because it's just way too fast. Already had too many of them already in the talk. So when it comes to that, I thought, well, how's the best way to describe it? And with this COVID, I've been sitting there doing a lot of camping, and it's like, threads and processors camping in CPUs is a bit like what goes on. Because if you come up with this model, you actually sit there going, well, if a process camps on the campsite, and it needs to get data out of its registers or it needs to get stuff out of its L1 or L2 caches, That's a bit like sitting on your campsite and going to your esky and getting something out. It's nice and quick, it's nice and fast. However, if I have to get something from RAM, well, I kind of got to get in my car and drive to the local shops. That kind of gives you the difference in sort of magnitude difference in terms of performance. Then if I have to go to disk, well, it's a bit like driving back to Perth and back again. And if I have to do network calls, it's like driving across Australia in comparison, and hopefully there's no COVID firewall stopping us getting there. So that gives you, now don't quote me on the kilometers and all the rest of it, but that gives you a sense of the magnitude of the performance differences of where you get the data from. So you need to keep that in mind when you're writing your software. So the first and most obvious thing is don't write small chatty networking. So don't keep driving back and forth across the nullarbor. That's inefficient, it's not going to work. The other thing is don't take lots of separate cars. In other words, don't do lots of small requests. All your requests have overheads. There's 38 bytes to all the packets that go over. And that adds up. If you're sending only 1 or 2 bytes, that starts adding up and clogging your network. You actually spend more time with overhead than you actually do it. So if you looked at it, it's a bit like this. You've got all these cars there, and there's all this wasted space. Now, your operating system kind of helps you out a little bit with this because it's got what's called Nagel's algorithm, or if you ever heard of the no TCP delay flag. What that basically does is it stops the packet for a moment, allows it to be filled with more data, and then sends it on away. It's a little bit more efficient. You think of it, it's a bit more like a train. Train pulls up to the station, waits a while, gets filled up with data, then moves out. And then it uses more efficiency on the network. Now, the nice thing is right back at the beginning of the talk, I told you Office 4 processes these things in parallel. I don't have to wait at the station. I've got parallel requests coming in. I've got lots of data feeding back into that train station. So Office 4 turns the Nagel's algorithm off and writes its own and actually avoids sleeping. And that gets it more efficiency through. Now, you've got to talk about threads. So threading is an important part about performance. And if you think about threading, it's a bit the same as camping on a campsite. When the thread comes in, it turns up on the CPU. It's got to warm up its L1 or L2 caches. It's got to get the things going. It's a bit like turning up at a campsite and unpacking and getting set up. It's kind of got to get itself set up and start processing. So when you look at the actual efficiency of using a thread, you've got the setup time and then the processing time. And when you're talking at this performance, this becomes important. Because if I start using multiple threads, I get more setup time. Now, I could use that and reduce the latency of the request and get the request going through faster, but there's overall more CPU use. It's inefficient. There's more setup time. There's more things setting up and then actually finally getting to process. It's more overall processing time. And this becomes worse when you try to do parallelism, which is creating more threads under high concurrency, because what happens is your request comes in, it's using a thread for the socket process, and then all your child requests come and steal the rest of the CPUs. And then what happens is all the rest of the requests are sitting there going, well, can I have a CPU? No, because they're all processing those extra threads you created. So actually, under high concurrency, doing parallelism and actually adding more threads ties up your CPUs and actually reduces your throughput. And made worse because there's more setups going on. So it actually becomes double worse. And then we get into thread coordination. So you've got locks. And locks are a bit like going to see the camp host and going, hey, can I use the camp kitchen? And the host is like, okay, let me check the schedule and I'll put you in and work all that out. That takes time. That's an overhead. Whereas you use atomic operations, which most languages now have, it's just a quick check. Is it there? Is it free? And do that. As an example in this, I had 2 uncontended locks in one of the tests that was running at 150,000 per second. Just removing those 2 uncontended locks, I got up to 450,000 a second. So at that type of level, you can see there are overheads. These things aren't cheap. And then it gets worse with the thread scheduling. Because what happens is when I lock up that thread, it goes to sleep. Now, being a good schedule on an operating system, it moves another thread in there, which then starts invalidating the cache and moving its stuff into the cache. And then what happens, another thread moves, and everything starts moving around again. And then everything needs to be set up again. And then everything starts creating overhead. And you go back to that problem of having lots of overhead to process through your requests. You're spending more time setting up your threads than you are actually processing. And furthermore, more CPUs is not always better. Because the more CPUs I have, the more that has to go across to RAM and actually access it. There's more contention. That all slows you down again. And if you're actually doing cloud, consider getting smaller, cheaper instances and having more of them. It's less, you've got more RAM to go around. Might be surprised. But the question is, What was the threading model that Office 4 used to get the 6 million requests per second? Basically, it just had one thread per CPU and just processed. The thread was hot and ready. The caches were all hot and ready and processing away. The request comes in and process out. It's a bit like the campsite already being set up by someone. You come in, enjoy the campsite, jump out. Most efficient camping you get. You don't have all the setup, tear down, and dealing with cleaning and all the rest of it. You just come in, enjoy the campsite, get out. And that's effectively what it does. It just runs a single thread on the CPU and processes away. But there's a gotcha to that problem. You've got callback threads coming back from the database. They want to come in and say, hey, I need to process the data. And then they say, give me a CPU. And then one of the socket threads has to move out. And then it goes in, and then the other callback comes in, another socket thread has to move out, and then they all start jumbling around. They start moving, and then you get that setup costs again, and then everything starts slowing down. Now, the schedulers do their best to minimize it, but you get that overhead. What you can do to improve that situation is you do thread affinity. Thread affinity binds the thread to run on only a single CPU, or a group of CPUs. You can set up the configuration you want. But basically, you limit what the thread can run on. So you limit that socket thread to only run on the one CPU. Now, this is a non-standard Java library. Check it out. It's quite a good library. But it has allowed me access to set up that thread affinity. And what this effectively looks like now is you've got the socket thread happily camping away, using the hot L1 and L2 caches, processing away. Callback thread pops in, uses a bit of the space in the side, does its processing, jumps out, the socket thread jumps back in. It's all still nice and warm and cozy and continues processing through. Very little overhead. And it just processes the data through as efficiently as possible. And big thing on this, be careful of doing this yourself. If the web server doesn't support it, you get into lots of fun problems with thread pools and then go into the wrong thread pools, and you can actually make the situation worse. You really need to understand what you're doing, or at least have your web server support this functionality. So, who here runs database connection pools? All right, who here has about 200 connections in the database pool? 100, 50, 20, 10. Well, the same problems here. Typically, and we're talking about the SQL variety of databases, we're not talking about the NoSQL, they're a different beast altogether. The SQL databases have typically one thread per connection because you've got the thread to process away and it gets into locks and contentions and the thread blocks on that and processes through. But we said we want to reduce contention because that gets better throughput. So what you actually want to do is minimize the number of threads. So you actually need to minimize the number of connections. Kind of counterintuitive, but if you can process requests faster, you can get more of them through. So if you actually look at Postgres or Hikari, which supports this as one of the Java top-end connection pools, it actually has this as your rule of thumb to start. Core count, which is not hyper-threading cores, it's actual core counts, times 2 plus the effective spindle count. Now, with SSDs, we have 0 spindles. So when we've introduced SSDs, we should actually be reducing the number of connections, not increasing them. Might be slightly counterintuitive, but the same thing applies. You've got contention, it's slowing everything down, and you're not getting the throughput you want. You want to get these things through quickly, and therefore you get more of them. So if you actually have a 4 CPU database, you should actually only have 8 connections to that database. Might be counterintuitive, but next time you have database performance problems, try reducing the number of connections and see what happens. You might actually be pleasantly surprised. But that's all been said, but what about the code itself? We're all developers, well, the vast majority may be developers, are interested. How do I write this code faster or more efficiently? So first thing, don't outsmart the compilers. There are multiple registers on the CPU and they all run in parallel. So compilers look for code patterns in your code to optimize the register use. So if you're looking at your code going, oh, what's that thing doing? And I've tried to do that to make it highly optimized. Your poor compiler is doing exactly the same thing going, how the hell do I optimize this thing? Basically, the rule of this is write readable code that camps well. It sits well, doesn't have overheads, it camps well, and it's readable so the compiler can see the patterns in it and actually optimize it. The question is, what style of readable code? So we need to look at memory management to have a look at this. Because when you look at memory, you've got the lower layer memory, which is all the physical memory in there, and then what happens is applications take buffers out of the memory. It doesn't take the full process full size, otherwise you couldn't run too much on your CPU. It only takes what it needs as buffers and then sort of takes more and more as it needs from the OS and then pages out. So effectively that's what it's doing, and then your compiler comes in and starts typing that memory. So it says there's a byte and there's a char which is 2 bytes and there's an int which is 4 bytes, float 4 bytes and references and so forth. And then we started adding OO on top of that. So basically you've got all these types, they're made private, and then you start accessing them by methods. And this may be slightly controversial, the functional programmers might have an issue with me, but another level up is that functions then are another level up which just don't have the mutate on them. They don't have the setter methods. They have all the other methods, but they don't have the mutations. So you just create new data all the time. Now, you can argue which way or for, but typically you get less bugs as you go further up. But also, when you're dealing with this level, you're dealing with mutation. You're dealing with changing data. You're dealing with mutations, which means locks, which means contention, which means all these bits and pieces on top of it. But with functional, you're just creating new things all the time. No new mutation. There's no actual real need to lock. You're just creating new things and you're processing it, and if new threads need to access, it's read-only memory, so go for it. Caveat on that, a lot of functional libraries actually use mutation under the hood. You just need to be careful of it. But generally, functional style code, which is just always creating things without mutation, doesn't need the locks around it. Generally. So what we actually do in high performance is we prefer functional code. But we can use memory to our advantage. So if I was to parse a HTTP GET request in an object or functional type of way, this would be the kind of thing you would do. You'd go, buffer to string and then check that the string starts with GET. Kind of a lot of operations in there. But I can kind of know that HTTP is US ASCII octets. So if I use the compiler typing, I can just check the first 3 bytes to go, oh, is the first byte a G, is the second byte an E, and there's the third byte a T. Now I've done it in 3 operations, a lot less. But that's not good enough. I can actually use the knowledge that the registers are 64 bits. That's 8 bytes. So I can read the long out of the buffer and go, right, let's mask out the remaining 5 bytes and then just check the first 3 bytes. Now I've done it in 2 operations. And if I need to check the put, 1 more operation. A lot less involved. And when you start looking at HTTP linear parsing and bits and pieces, you can actually use this to your advantage. You can sit there and go, right, read out 8 bytes, you mask out the bytes, 0 out the bytes for the character you're looking for, trigger an overflow. If there's an overflow bit, because all HTTP ASCII octets is the last 7 byte or 7 bits of the byte, and the top end byte is 1 byte, it triggers an overflow into the top end byte, mask that out, and then check if there's an overflow. If there's an overflow in every byte, your character's not in there. So instead of having to do a for loop, which is 8 operations and 8 checks, which is about 16 operations in total, you can do this in 4, quarter of the effort. And this is what's called bit twiddling, if you've ever heard the term. And there's bit twiddlers out there, quite literally. And you can see sites. A lot of the universities have sites that actually show you all bit twiddling tricks and so forth. And this is very useful in shortcutting repetitive HTTP processing. Now, in Office 4, it's used only for that. The rest of the application server is using functional compiler-optimized code. And the thing on this is typically there is little value bit twiddling your application logic because the compiler will come in and optimize it for you. So the moral of this is write functionally styled application code that the compiler generally optimizes for you. So, in summary, hardware is about fast, software is about efficiency. Understand the hardware, at least at a logical level. Kind of understand that map of Australia and where the cost is of getting the data. Code design is more important than coding language. When I start hearing people complaining, this language is faster than that language, I'm like, it's how you write the code and manage it is more important. Minimize the number of threads, ideally 1 per CPU. Minimize the number of database connections. You may be very surprised when you do that. Consider atomic operations over locking. Caveat on that, if you've got critical sections, don't do that. Things, there's a disclaimer on that, but try and use algorithms that use atomic operations rather than critical sections. More often scaling instances is better than more CPUs because you're not contending over RAM, and consider functional programming practices because of lack of mutation. Scale across CPUs. on that amount, thank you, and I'm happy to take questions if time.